Okay, oxide chemistry. Okay, I believe we made it through here. I believe we're pretty much made it all the way down to this midsection. We ended with the reaction at the top, very top. That reaction is no good. You can't have a strong nucleophile and acid in the same reaction. No good. You're going to have acid. The only nucleophile you can have is weak nucleophiles. Your halide anions do count as weak nucleophiles here, but they can exist with strong acid. Okay, now we're moving to basic conditions. First off, I thought ethers were unreactive under basic conditions. Yes, most ethers are. Regular ethers, THF solvent is. But epoxides are reactive under basic conditions because of the ring strain. You do not need H+ with epoxides if you have a strong nucleophile. What are examples of strong nucleophiles? And I don't have anything to clean this board with. I don't know why it all of a sudden would be like this. Anybody have any insights? Okay, so what type of strong nucleophiles will we see being used with epoxides? One is, well, what have we seen before? Acetylide anions. We can make acetylide anions by deprotonating a terminal alkyne, such as with sodium amide or n-butyl lithium. These are two common textbook bases. We've used this one here already this semester. We can deprotonate, make acetylide anions, strong nucleophile. Now we can put it in epoxide. This is the simplest of epoxides, right there. 2 carbons, that's it. Simplest of epoxides you can have. It's called ethylene oxide, by the way, because that alkene, while you might call it ethene, it goes by the name ethylene. And if you add the oxygen to ethylene, you have ethylene oxide. That's this kind of slang name that's called. Ethylene oxide. Okay, these electrons will attack one of the carbons, kick the oxygen off. It does not need to be protonated. Either carbon's the same, these electrons attack here, kick the oxygen off. What do we get? We get this right here, and this is an SN2. Nucleophile. This was the nucleophile here. We attack carbon, that left, so we nucleophile carbon, carbon, O. And that'll be an O- when it takes on the third lone pair. So this nucleophilic addition to this here gives this here. Again, we're seeing the oxygen leave without it being protonated, without it being made to have a positive charge. We've never done this before. It can do this because of the ring strain of the epoxide. The ring strain is relieved, and so all that relieving of that energy builds into lowering the transition state, makes this possible. We get this. This is an anion here if you follow your mechanistic arrows. To go neutral, we have to supply a proton, but that's in a separate step. Usually you supply acid, although water may theoretically work or be seen sometimes if you're extracting. Typically, though, you need acid, your favorite acid source. Then these electrons will react with the acid. Now we have the OH, and this would be your final neutral product. You cannot have the H plus with your strong nucleophile. They're not compatible. So two separate steps. Questions about that? Okay, what other types of strong nucleophiles may we see? What about just plain alkyl anions? That up there was the alkyne. Carbon was on the alkyne triple bond carbon. What about a plain alkyl? Well, first off, it's very hard to remove an H from just a plain alkane. Now this is just R, but if you just take something like butane, try to remove an H, what base are you going to use? There's no base strong enough to remove an H from butane, okay? To make, maybe this, where you remove one of these H's. Butane has no acidity at all. The alkyne has some acidity. We talked about that way back at the beginning of Organic 1. So how do you make these? Because that's what we're talking about. Alkyl anions, not alkenyl or alkynyl, just plain alkyl. This is very difficult, pretty much impossible. There's a tricky way to do this though. We can make this from something like this. Instead of removing an H, we can essentially remove a chlorine, but it's not coming off as Cl+. But we can do this. So how in the world can we do that? Well, first off, this is your R group with a halogen. R group with a halogen. Halogen can be for any of your, chlorine, bromine, iodine, typically not F. That's not overly important right now, but it's just information here. We can react this with a metal. Okay? Group 1 metal or group 2 metal. Group 1 metal, for example, would be lithium. That's very common. I think we have the look over. That's just all introducing it. We can look over and see the examples. Before we turn the page, we really need to turn the page. I wish it was all here. We could look at them both. Let's go ahead and turn the page and look at the examples of this. Now in my examples, I just have a bromine there. I also have one less carbon, but it's the same thing. Okay? If you react with lithium, you'll get this guy plus lithium bromide. Now this is shown covalently. We can also show it ionically, and it would be like that. Okay? And here's your anion, which I said we can make, and lithium would be plus. Now, even though in Gen Chem you're told that group 1 doesn't make covalent bonds, actually some organic with metals can be covalent. The structure is often sort of in between covalent and ionic. Okay? So sometimes you will see it shown like this. But for us, let's always consider it ionic, because this is going to help us reinforce that we have the carbanion, and thus we have a strong nucleophile. Now this also produces lithium bromide. So that's why you need 2 equivalents of lithium. This is lithium metal, oxidation state of 0. This is commonly done in like an ether solvent, which is unreactive towards a strong nucleophile, like we said before. The mechanism for this is redox. The lithium is being oxidized. The carbon is being reduced. And because it's a redox mechanism, it's not easy to show. It's probably a radical reaction. We're not going to show mechanism. Okay, the more common one here of these is using magnesium. Now that's group 2. With magnesium, you only need one equivalent. With magnesium, you get only this product. Now, if we show this ionic, what's typical charge of magnesium? 2 plus. What's typical charge of Br? Minus. And thus, we have to have one more what? One more minus to cancel to make this all neutral. That's because this here is like this. If you show all this ionic, once again, you get your carbanion. And the magnesium is 2 plus. This is often shown all together, where this certainly looks covalent. That could just be formula. Both of these are essentially carbanions. And they're going to react like that. Now, I can say something about the mechanism, some terminology. This is said that the magnesium does an oxidative addition to this alkyl bromide. An oxidative addition. First off, it's added. It added between the carbon and the bromine. The magnesium was also oxidized because here it's 0, now it's 2 plus. And so the magnesium has done an oxidative addition. If you look that term up, you'll see lots of stuff about it. And actually, many metals, particularly ones way over here, way over there, even some more over here, many metals can do oxidative additions to alkyl halides. They'll insert between them. That's a magical reaction. I think the first metal that was ever discovered to do this, I think, was zinc, back in the mid-1800s. Okay, when you do it with magnesium, that's the most common these days at introductory level. The reagent you produce is called a Grignard reagent. That's just called an alkyl lithium. No special name. But Grignard is the one, Victor Grignard is the chemist, I believe it was French, who really showed that magnesium does this and then really used these products as nucleophiles, carbon nucleophiles. And he actually won the Nobel Prize about 110 years ago. Okay, so making Grignard reagents and understanding their use. They're essentially carbanions. Questions about these reactions? So this is how we get to the carbanions. Instead of removing an H, we do this oxidative addition of a metal to the alkyl halide. By the way, these in general are called organometallics because they have an organic portion and a metal portion. So Grignard is a very common type of organometallic. Previous page, make sure we saw everything. All these organometallics are essentially R-, very basic nucleophilic. Importantly, neither can exist in the presence of acid or acidic proton or just plain protic solvents. For example, if you take a Grignard reagent, have it in the presence of ethanol, it'll just take the H. Leave it behind, it'll take the H and you'll just produce this. You cannot use these in protic solvents. You have to use a solvent such as THF or ether, like a hydrocarbon solvent or ether solvent. No protic solvents. No water.
So
water will destroy a Grignard reagent.
it's all the first. So you could use sodium.
Sodium is sometimes used.
Okay. So could you use sodium hydride?
Mechanistically, how would that work?
The sodium and the hydrogen would dissociate, and then you could just
Well, I mean, how would it work from there?
the same way that the lithium.
Well, in sodium hydride, sodium is already positive.
Oh, okay.
You gotta have it. Sodium ion can't do an oxidative addition. Because it can't be oxidized anymore. These are metals. There are sometimes when, if you have two oxidation states, the lower oxidation state can do an oxidative addition and become the higher one, but sodium only has one oxidation state. Okay. Some metals do this better than others. Some metals make your alkyls dimerize. Sodium may be more prone to doing that. These are the most common. We've used N-butyl lithium before, many times even in organic 1. This is how N-butyl lithium is made. You take butyl bromide, react it with lithium, you'll get N-butyl lithium and lithium bromide. Okay? You don't make it by removing an H. You do this oxidative addition thing. Okay, let's look at products. Right here. Now this is not butyl, this is propyl. But this reacts with this to give boop, boop. Okay? If you can't see, just yell and I'll try to do better. I mean, it gives that. Again, this is really, if you show it ionic, it's that, right? But here's your nucleophile. 3 carbons, don't lose track of your carbons. Then this text over here. We didn't say it on the previous page, but I'm sure it was written. Is this mechanism going to be SN2 or SN1? Strong nucleophile is always SN2. We learned that in organic 1, right? Strong nucleophile is going to be bimolecular, right? Okay, SN2, always SN2 with strong nucleophile. You only do SN1 with epoxides or ethers when you have a proton. There's no proton here. SN2, since it's SN2, which carbon are we going to attack, left or right? Right, electrons up, and we get which bond did we make? Right there. I'd like to highlight the bond. 3 carbon alkyl, attack that carbon, kicked off the oxygen, it's still bonded here. No change in stereochemistry there. There's that. What does appropriate workup mean? Okay, appropriate workup is to make this neutral. What do we need to make that neutral? What is appropriate workup going to consist of? I think it was on the previous page. What did we add?
Acid or water.
Acid. Okay. Like H+, your favorite acid. What is it going to do? This attacks H+. What do we get? Well, we just get the same product, but it's got the H on there. Okay. I'll redraw here, but in the future I won't redraw it. Okay. So we just get this product, we made this bond here, the H came from workup. Questions about that one? Okay, iodobenzene, magnesium, PHF, what is that going to produce? Magnesium does oxidative addition between the carbon and iodine. We get this here. We know this is really what? It's really that carbanion. It reacts as if it's that. That minus, I minus, Mg2 plus. This is your nucleophile. We're going to attack on left or right. These electrons attack here, kick the oxygen off. What does that give? I'm just going to draw that ring as phenyl. This is the benzene ring bonded to this carbon. We get this product here. We're going to make that bond there. And then work up. Well, just put the H on. Make it neutral. Except H plus. Question?
Would there be an inversion on the side that you attacked?
Yes, I did inversion.
Oh, okay. I see it. Yes.
Yes, inversion, right? It's inversion. SN2 always has inversion. We did not do any inversion over here because there's no chemistry over there. That just opened up.
What happens is you can do this again, right? So the nucleophile is acting from the downside, right? From here, right? So that's going to make the wedge go up.
Any questions about that inversion?
Position for the but it goes from down to up because the nucleophile is at the bottom side. But it's still
This carbon was inverted.
it's acting from the position now, but it was inverted and then the wedge is changing.
Do you look at the epoxide?
That's why doing like on switching is not.
If you want to do that, is the new thing here, priority is 1. 1, carbon on this 2, 3, H in the back. This is R. Assuming that this is plate, okay, does this have the same priority as oxygen when it comes in? It would. Phenyl is 1. That is all that with oxygen. See, actually, I don't know that it would. Hold on. I don't know that this takes priority. This still may have priority, or this may now have priority because this carbon is bonded to oxygen, but this carbon is not.
Yeah.
I don't think it works just going from. That may still be R over there, but it's inverted. I mean, I came in from below, kicked the leaving group off.
But wouldn't it push that forward carbon back then?
Which forward carbon?
The one that's already
No, because you're not attacking
on the
from
left.
counter page.
No, why would it push you back? That'd be a very bad bonding.
Okay. I'm just confused because I don't see the inversion. Because of that prior, if that's still 1.
Okay, here's oxygen's your leaving group. Here's your nucleophile. How does it come in? Does it come in here? It comes in behind it, right? Okay. Well, here the oxygen is straight up. Now it's also bonded over here. Okay, I don't have to have another bond here. They're straight up.
Flip around.
Let's make it right here. Pretend this is bonded here. Okay? This methyl is forward. Okay? How does a nucleophile come in? Backside, which is here. Okay? When it comes in and makes new bond, it kicks the oxygen off. The oxygen opens up, it's still bonded over there. But when it does that, what does it do to the methyl?
Pushes it.
Does the methyl all of a sudden go back? No, the methyl just goes this way. It goes up. It's still forward. It's up, but it's still forward. I think y'all are used to seeing the methyl like this. It's forward, and when this comes in,
Yeah.
pushes it back. I'm just turned. It's the same thing. It comes in, it pushes it back, but from your view, it's forward. It's still forward. It's just forward that way now. You got to see that. And there's a number of ways to draw this. That's inversion. When inversion comes in, what happens to all this stuff? It goes the other way. Depends on your view. If you want it to go from bold to dash, you need to look at it this way. When it goes back, when the thing come in pushes it back, then it will be back. Okay?
All right.
You need to think about that. It was inverted. That is, the nucleophile came in from the bottom because the leaving group was straight up. Okay, just put the H on, no change there. And actually, if someone wants to do R and S, I think this is R. I think that's probably still R. We'd have to think about it because when you do inversion, R does not always switch to S. That is not the definition of inversion. 99% of the time it does, and we've always done that. Definition of inversion is just this, like an umbrella, being pushed the other way. That's inversion. Question?
So would it be wrong if instead of doing the wedge up, we just did it like dash down?
You mean draw the phenyl up in this?
No, like if we were to keep the phenyl in the same place, but then like how the methyl is in the original equation, in that same position, if we just did it as a dash instead of a wedge, would that be wrong?
I'd have to look at it. I mean, you can draw this with a dash. I mean, I could flip this totally around and make it all change. I would encourage you to look at and understand what inversion is and how you just see it. I mean, it just comes down here. We're just doing it from the bottom to the top instead of from the side to the other side. That's inversion. You can think about it. And you got to be leery about pitfalls. Beginning students think, oh, inversion is always going from bold to dash. No. It all depends on how you show it. Okay, we'll do more examples. One below. So those are standard. Alkyls. Those were alkyls. That was the heading. That must have been B. What about C? Amines. Well, amines are strong nucleophiles. They're strong enough to do SN2. Okay? Where are we going to attack? Top or bottom? Bottom. Attack here. We kick off the oxygen. Okay. The leaving group is forward. So how does the nucleophile come in? Comes in from the back. So here we're going to draw a dash. So now the amine comes in here. Just draw out our bonds. There's no lone pair. That's a positive charge. This just opened up. There's no change in the top stereochemistry. See here the leaving group is bold or dash. Up there the leaving group is in the plane. So that means the new thing comes in the plane, but just low. Okay? Here's your product. How do we can go neutral here without adding anything, because here we have a built-in H+ source. That nitrogen wants to get rid of H+. This oxygen wants to take it. Okay? Mechanistically, I could show this taking one of the H's, leaving the lone pairs behind. But at this point, usually we're going to just call it H+ transfer. Hot potato transfer. Okay? And we're going to get a product has the OH, and then the nitrogen is just going to have one H, and the lone pair is there. We only transferred the H+. The electron stayed on the nitrogen. This is probably intermolecular. That is, this could act as a base internally and take it, but most likely this takes the H from another molecule. Okay? Because all these, there's a million molecules and they're all real close together. So if I need an H, I don't have to take the one that's bonded to the nitrogen in my same molecule. I can take the H from another molecule. This can take the H off of a nitrogen from another one of these. Okay? It's called H+ transfer, protons transfer. The books, sometimes books call it differently. We'll be doing a lot of H+ transfer this semester. Okay? And you don't need to show a mechanism because it's probably intermolecular. Question? Marvin?
Since the nitrogen is a base and it's in acid, isn't it going to keep its hydrogen?
Hold on now. There's no acid.
Oh, I'm sorry. I was looking at the H+.
There's no acid here.
Transfer. Okay, never mind.
There's no acid here. You want to? This is an acid-base reaction. You want to judge this by pKa's? pKa's. I mean, the pKa of a protonated amine is about 10. What's the acid now? Which functional group has the acid now? Here's the H. What's the pKa of a typical alcohol? About 16. You need to know these pKa's. Which is favored, 10 or 16? The weaker acid, 16. That's favored over this. That's why we came this way. Okay? All right. So that involved, we didn't have to supply a proton from an external source. The nucleophile, because it started as neutral, once it became positive, one of these protons became available as the proton source. And we had an internal proton transfer, H+ transfer. Okay, the ones below I think I want you to do on your own. They're just examples. A two-step synthesis. What does MCPVA do to the alkene?
Epoxide.
Okay, so we start thinking about multi-steps. One below, terminology. When you're using strong nucleophiles, the mechanism is always SN2. When you do an SN2, you always attack which carbon? Or least sterically hindered, because SN2 is largely governed by sterics. Of course, if they were both tertiary, you'd have a problem. But you don't do SN2 at tertiary sites. Hopefully you won't see one like that. Okay, use of epoxides in the multi-step synthesis. Epoxide is a great source of 2 carbons and an OH upon being attacked by a nucleophile. These reactions, we ended up with nucleophile, carbon, carbon, OH. This was originally the nucleophile. Carbon, carbon, OH. The other reactions we did, they all ended up having a nucleophile, carbon, carbon, OH fragment there. Repeat it with me. Nucleophile, carbon, carbon, OH. That's the result of an epoxide reaction. Okay? Thinking backwards. Terbutaline, okay? Used as a drug to treat premature labor in women. Can you synthesize this by an epoxide reaction? Using an epoxide as maybe an intermediate. Do you see what could potentially be a nucleophile carbon-carbon OH? Yes. I know amines can be nucleophiles. I can have a nucleophile carbon-carbon OH. So from that, I can separate out the nucleophile from what would have been the epoxide, and I can go backwards, retrosynthetic analysis, and say, hey, I could go back to That epoxide with the phenol groups both being meta, these are okay. And coming forward, what would I react this with? That amine. Now I could say I'm going to use a negative nitrogen. But usually with nitrogens, the neutral nitrogen is sufficient. Now look at it. Would this amine react with that epoxide to give that product? Yes. This is a good nucleophile. Which carbon is it going to attack? Left or right? Attack here. Kick that off. What does that give? Well, it's going to give that structure. I'm going to call all this just aromatic. Okay? It's going to give aromatic. The nitrogen is now bonded to this carbon. That's a plus. Oxygen opened up on this carbon, opened up as a minus because it's got 2 lone pairs. When this moves on to oxygen, that has 3 lone pairs. We just made this bond. Nucleophilic addition to the epoxide. Opening the epoxide, what's this going to do? This looks like an acid. It looks like H3O+. Oxygen with an H+. So nitrogen with an H and a positive charge. It'll supply an H to this guy, which looks like a base. That looks like hydroxide or something. You're going to get this internal acid-base reaction called H+ transfer. And wouldn't that give that product over there? And how many lone pairs are on the nitrogen over there? 1. You got to understand that when this transfers, I've seen some students that think there's no lone pair here. Of course there is. If you get rid of the H, the 2 electrons stay behind as the lone pair. Understand what H+ transfer is. We will do it a gazillion times, especially the second half of the course. So does that make sense?
Mm-hmm.
I don't see any other reaction that you could use. I think that's really the only one. So and that's most likely how that compound is made. Probably epoxide precursor. So there's an example. Nucleophile, carbon, carbon, OH. So look for that. Now on the next page or 2, there'll be more multi-step synthesis. Okay? Epoxide is very versatile. Now, one thing to caution, you got to keep in mind. You can then do chemistry with this OH, right? So it may not be as obvious in what you're looking at, but you need to back it up. And then you see the alcohol, and then you say, aha, I can make this from an epoxide, and then I can continue on to maybe that. Okay, polymerization of epoxides. Epoxides can be polymerized. Some of you have probably heard of epoxy glues. Okay, you polymerize it and it turns into the glue. Okay. Ethylene oxide, you can even polymerize it. If you're acting with just aqueous hydroxide, this might be a simple monomer that we could predict. But you can also get this polymer, which has a repeating unit in parentheses where N is a huge number. How can we get this? Here's our nucleophile. Hydroxide and water. Which carbon do you want to attack? Okay, it doesn't matter. We'll attack here, kick those off. What does that give? Nucleophile attack carbon, kick off the oxygen. Nothing really new there. How can we get this monomer then? Well, proton transfer would just take the H off here. We need another proton. Well, water can actually supply a proton. Now usually you just do this with acid, but water can in certain cases, and here, I mean, you don't have any acid, but we can take the H from there, leave these behind, that gives that, right? Plus what? What did we produce? We produced hydroxide. So hydroxide was actually a catalyst here in this reaction. And the reactant was actually water. We consumed the water. If you look at formulas, what's the difference in formula between the two? This now has H2O added to it. Okay? We added water to that, and that's how you got that monomer. It was actually catalyzed by hydroxide, because water is not a strong enough nucleophile to add here. It's not a strong nucleophile. That's how you get monomer. How would we get polymer? You get polymer, instead of this just picking up proton, what if it attacked another starting? What would that give? This could attack here, open that up. What does that give? This oxygen is now bonded to that carbon, carbon, O. Nucleophile, carbon, carbon, O. Now that could pick up an H and become OH, but until it does, it's O minus. So nucleophile, carbon, carbon, O. What could this attack? This could attack here. You get the point? And you just keep on going. That's how you get polymer. It just keeps on reacting with itself instead of picking up proton. Now you can do these different ways. If you want polymer, you do the reaction a certain way. If you want monomer, you do it the other way. Well, either way, it's kind of tough, because even if you want to make this, it's always prone to polymerization if you don't do it right. How do we get this? Well, what is our polymer? It's an OH with a carbon-carbon O. Carbon-carbon O. If we keep going, that's what it'll be. It's an OH with a carbon-carbon O. That just repeats a gazillion times, and you can eventually just end it, where the end fragment, the carbon-carbon O, picks up an H. Now, polymers are never completely defined. There's always a little ambiguity in what's the true structure. But do you see the repeating unit? We only did it a couple of times, but carbon-carbon O, carbon-carbon O. It just keeps repeating if you keep going. So that's how epoxides can polymerize. They just keep reacting with themselves. Does that make sense? In epoxy glues, you kind of start with something like this. Anybody ever use those glues? You add something, and it's like you add this, and it starts making the polymer, and then the polymer comes thick and gluey. Sometimes that's called like the curing agent or something. You add something to make it do something. These glues like that, buy at Lowe's or Walmart. Next topic. This is sort of miscellaneous, but it's important biological application. Thioepoxides. That's where the oxygen is a sulfur instead. Okay? Where do these come up or raise their ugly heads? You ever heard of mustard gases?
Yeah.
War gases. A mustard gas looks like this. There's different ones, but this is a common one. This sulfur can come in here and kick that chlorine off. Internal SN2. That can happen pretty darn easily. Okay? Now this, like when it's being stored, this actually may be in equilibrium. Okay? Because that chlorine can maybe come back and attack and kick the sulfur off. But when this does, what do we generate? a three-membered ring with sulfur analogous to oxygen. But not only that, the sulfur has a positive charge from having 3 bonds. So the sulfur is a good leaving group because of the ring strength, but also its positive charge. That's a very reactive substrate. Nucleophiles from your body, such as DNA or proteins, all these have nucleophiles like amino groups. The nucleophile can then come in here and kick that sulfur off. And that's a very easy reaction because of the ring strength and the positive charge on sulfur. And so these things will start reacting with all your biomolecules, and it'll just lead to very bad damage. Okay? You held this stuff. Okay? Or you can react with water. The other thing that these produce is when a nucleophile reacts, typically it produces HCl. Because you got that Cl minus, this is going to lose an H and produce HCl, and the HCl can also cause problems. You get the HCl in your lungs. So you got bad problems. These things are not good. But do you recognize and can you understand some of the chemistry that's going on here? What makes them not good? Any questions about this chemistry? This is just sort of spontaneous. It doesn't take much to make that happen. Okay. All right, multi-step synthesis. You can read about the cow over there. Please be looking at these. Let's see if we can think about this one real quick. How would you make this compound by multi-step synthesis? This one here. We'll be looking at alcohol oxidation next time, most likely. That was going to require an alcohol oxidation. How about here? What can we back this up to? Well, what's our main functional group? Ether. How do you make ethers? Back this up to maybe the phenyl.
Alcohol.
Back it up to that, plus react it with what? Maybe ethyl bromide? Would those two react to give that? Okay, I'm hoping you can see. So how do you make ethers? Well, this is a way. There's another way you can make it, okay? And so you could come back to another ether. This is essentially not going to be OH because we know if we're going to react these two, first we have to deprotonate. Okay? But we can back that up to this. Now, what are we doing? Synthesize these from bromobenzene. Let's start with that. Well, aha, this is an OH. Can we do nucleophile carbon-carbon OH? Could we make this bond? Having 2 carbons and an epoxide, what would we react it with? Just a benzene nucleophile. Coming forward, we're going this way. Would these two react to give that after appropriate workup? Do I hear a no? Yeah, these two would react with appropriate workup to give that. How do you make this? Well, that's just generic for what? And that would be like your magnesium bromide, your Grignard. That's like a Grignard reagent. How do you make Grignard? Like bromobenzene reacted with what? Okay, we started with bromobenzene. Make Grignard, reacted with this epoxide, that'll give this after appropriate workup. Then you come in here and you do an ether synthesis. So I went through that pretty quickly. We're here at the end, but please take a look at the others. Start thinking about multi-step synthesis. Any questions about that one as we finish up? Okay, for those that want to get the workbook fixed for the Wednesday lab, please stop by today at 2:30 to 3:30. Get your workbook fixed. Thank you.